Okay, so hello everyone. As you can see, I'm very stressed. So if I speak too fast or not in the microphone, you can tell me, which will probably happen soon. So I'm going to speak about the study of cosmic ray acceleration regions through their chemical composition. My name is Aimie Clément, and I'm working with Valentine Waclam, Pierre Gratier, and Marianne Lemoine-Goumar. Okay, so cosmic rays. Cosmic rays are high-energy ionized nuclei, mostly protons. They are mostly relativistic, but a small fraction is also ultra-relativistic with energies up to 10 to the 20 eV, as you can see on the cosmic ray spectrum here. So the fundamental questions when speaking of cosmic rays are where do they come from, how they are accelerated to such high energies, and what is their impact on the interstellar medium. So speaking about the interstellar medium, it is composed in terms of mass of 99% of gas, so mostly hydrogen, a bit of helium and other stuff like carbon and oxygen and stuff. So what I'm the most interested about are the dense clouds that you can see here on the interstellar matter cycle. So they are quite dense for the interstellar medium, and they are also cold. A lot of chemical reactions are happening there. So whether it is in the gas phase or on the grain surfaces. And what I'm the most interested in are the cosmic rays. So the cosmic rays are responsible for the ionization of the molecules in the ISM. So we are going to speak about the ionization of H2, which is the most abundant molecule. And we speak about the H2 cosmic ray ionization rate. And so a cosmic ray will ionize H2, which will give H2 plus, and then H2 plus will become H3 plus. And H3 plus is very, very important for the chemistry, and it will contribute to the increase of the molecular complexity in the ISM. So the region that I am studying is the HB3W3 complex, which is located at about 2 kiloparsec in Cassiopeia, in the Heart Nebula, because it looks a little bit like an anatomical heart. I don't know if you can see it. But so W3 here is a giant molecular cloud on the very active massive star-forming region. And HB3 here is a supernova remnant, so which is quite old, like 20 to 30,000 years old, and it is interacting with the cloud here. Cosmic rays, as I said, the mic. Cosmic rays, as I said, so what we want to do is to use different chemical tracers of the ionization to try to constrain the cosmic ray ionization rate. So we will do some chemical modeling with Nautilus. I will speak about it just later. And we also have a lot of observations, so in radio. So with the IRAM 30 meter and the YEBES 40 meter. So I will mostly focus here on the two single pointings that we did on the point A here and B, but I will speak about it later. Nautilus, so a few of you already talked a bit about it, but it is a chemical free-phase gas grain chemical modem. It uses more than 1,000 chemical species and tens of thousands of chemical reactions. And it allows to compute the gas and ice composition as a function of time for a set of different physical conditions, including the ionization rate. And it allows to get the time-dependent abundances of the molecules. So the goal here is to reproduce the observed molecular column densities to try to constrain zeta, so the ionization rate. It's a very busy slide, sorry. But to do that, we are working on a code which is called invert spectra, and it takes as an input the radio spectra, and then using different inversion methods, either optimization or sampling without priors in LTE or in non-LTE, we are able to extract the physical parameters related to the molecules, the density, the temperature, the size, and also the molecular composition in terms of column densities. So we did a preliminary analysis on the 30-meter data on HC3N, and it allowed us to conclude that the sources A and B that we observed are quite dense and cold. So we then used this molecule HC3N as a prior distributions to help the fit for the other species. And it's outside of the of the box. So it allowed us to extract the column densities for all the molecules in LTE or in RADEC when we have the collision rates. So here is a preliminary plot about the abundances that we extracted from the 30-meter data. So we detected 38 molecules, including some isotopologues. So we did just a quick comparison with TMC1, so which is the torus molecular cloud. And we see that for some species like these ones, the abundances are very similar, but they are very different for others, like this one, for instance. But now what do we do with that? So we wanted to know if we could constrain the ionization rate only with the chemistry. So to do that, we did an exploration with Nautilus on a grid of parameters. So we chose to vary the density, so between 10 to the 4 and 10 to the 7 per centimeter cube, the ionization rate between 10 to the minus 18 and 10 to the minus 15 per second, and the time, so using the time steps of Nautilus. And as a first attempt, we tried to use it on simulated data. So for the set of observed molecules that are also in Nautilus, for a given value of the uncertainty on the abundances, and for a given time, so quite evolved, and a given density, so quite dense. And we wanted to check if we could discriminate between two zeta values, so one low and one high. So the goal is to get the posterior probability distributions for the three parameters for a given observation. So we have, it's not very nice. Well, so we have three parameters. So we want to explore the 3D probability distribution. So we are using a code which was developed by Lydie, who did her internship at the lab a few months ago. So what you can see here are kind of triangle plots that help us to visualize this 3D space. So on the diagonal here, you have 1D probability distributions, and here, so outside of the diagonal, to 2D. So if you try to discriminate as it is, we see that we can already discriminate between a low zeta and a high zeta, but it's not very well beautiful. So what we try to do is to add a prior on the density, so prior that we extracted from our observations. What we see is that it's better now. And we can really discriminate between the high and the low zeta, and that adding a prior on the density reduces the uncertainty on the other parameters. And I forgot to mention that the dashed line here are the parameters we choose to put as an input and that we try to reconstruct. So, as I said, we are able to discriminate between the two zeta value on simulated data, but we did that for a low uncertainty on the abundances. So we did that for a value of 0.3, so which means a factor 2 on the abundances. We tried to do it for a factor of 10 on the abundances. We see that it still works. We can still say that it is a low zeta. And even with a factor of 100, we can still say that this is a low zeta. So we were happy about that. And the next step on this work would be to use it on the real observational data. So I will do that soon, I hope, when I have the time. And now I'm going just to speak about something else, because another part of my PhD work is in gamma rays. And cosmic rays are also very important in gamma rays, because when a proton of the cosmic rays will interact with the proton of the matter of the ISM, it will produce a neutral pion that will then decay into two gamma rays. So studying the gamma rays gives us information on the cosmic rays. So I used the Fermi-Lat telescope. I had 14 years of data, and I will not speak too long about it, but I did an analysis of this region, and what I concluded is that to reproduce the gamma ray emission, I need to divide the molecular cloud into 5 boxes. And what's interesting is that when I study the gamma ray spectra of these boxes, I see that they are very different. And especially these two here, so the number 2 and the number 3, are significantly different. And that's interesting because the A and B pointing that we have with the 30-meter are in one of these boxes, so in 2 different boxes. So what we expect is to find different ionization rates in these 2 boxes. So we'll see when I finish the work, of course. I'll tell you maybe another time. And that's already the conclusion. So to conclude, I did a study of the impact of cosmic rays on the chemistry of the molecular cloud using radio data, using chemical modeling with Nautilus. What we want to do is to reproduce the observed molecular column density with Nautilus to constrain the ionization rate. So we did a test on a parameter grid, and we were able to discriminate 2 zeta value on simulated data. So now we want to do it on real observational data and really link the 2 parts of my PhD, so astrochemistry and gamma rays, to try to constrain the zeta and understand better the cosmic rays in the regions. That's it.